Welcome, welcome. If you'd like to get started, people watching this on YouTube are, wondering when it's going to start. Thank you for coming today. We are honored to have the project scientist for the Gaia project visiting us today, Dr. Timo Prusti. We'll be taking him out to dinner tonight. He'll be around tomorrow in the morning and a little bit in the afternoon if anyone would like to talk to him further. He is the Gaia project scientist, but he's been working on satellites for quite a while. He joined the European Space Agency in '93, working as an astronomer for ISO, and then assumed the duties of the ISO archive scientist. In 2000, he moved on to the Herschel project to join the science team there, and later became the deputy project scientist. And he's been working as the Gaia project scientist since 2007 or so. And those of you who remember your Greek mythology know that Gaia was the offspring of chaos. So we're sure today that we're going to learn something else about Gaia, not chaos.
Okay, thanks. And thanks for the invitation. And instead of creating chaos, maybe Gaia will bring some order to the universe, or at least at the Milky Way level. Let me just directly start summarizing everything so you get at least the overview of what Gaia is all about. So we have made a sort of science slogan of science with 1 billion objects in 3 dimensions, which already hints at the big sample. We are going to get distances, and we are going to do science with it. It's an ESA cornerstone mission, and clearly there is a heritage for astrometry in ESA, so it's really building a lot on the Hipparcos heritage. A lot of people who have been working in Hipparcos are still in Gaia. It's really astrometry why we go to space, because the astrometric part you can only do from space with that accuracy. But we also do photometry and spectroscopy. And the photometry, we actually have to do it because we need the colors for the stars to do accurate astrometry because of the color corrections in the optical path within Gaia. But if you do photometry, you might as well do it properly so that you can do astronomy with it. And spectroscopy is something which was a lesson learned from Hipparcos. I think so far about 100,000 Hipparcos stars, about 50,000 have been done properly spectroscopically. So people had very quickly through the idea that if you don't do it with the mission, you just never do it. You will never be able to do it. You have to do it at the same goal. Gaia is a little bit peculiar in the ESA program in the sense that there are no instrument building institutes involved. It's all built by industry. And the main reason why this was chosen was that whatever you do in the service module facing the sun has an impact to the observations in the payload side. So there is such a heavy system engineering impact in Gaia that it was considered much easier that one entity is fully responsible of all the interfaces and all the elements of it. ESA does the management of Gaia, and we do the operations, really the conducting the spacecraft. And then where the scientists are coming into a game is the data processing. So we have a data processing and analysis consortium consisting of scientists in Europe, and they take care that actually the telemetry is converted into something what the astronomers are really interested in. We launched 13 from Kourou with the Soyuz rocket. We took a little bit longer than half a year to finish the commissioning phase. And now we are sort of into first year of the 5-year nominal operation period at L2, 1.5 million kilometers away from the Earth. And for the data, the first release we expect summer 16. But the science alert stream, although in a validation mode, has already started. So there are already people looking for Gaia follow-up observation. I'm not going to go into detail much of science because I think that's something what we do when the catalog is available. But just mentioning very briefly where the main drivers are coming really from our Milky Way galaxy, the structural dynamics and the star formation history. So you have to know where the stars are and how they are moving before you can really tell. We actually don't know how our Milky Way really looks like. It's clear for stellar astrophysics that if you don't have distances to stars, you do have a serious handicap. For binaries, we just do full sky imaging at the Hubble Space Telescope resolution. So anything what you can resolve in Hubble, we do it for the whole sky. Plus, all those binaries which have such a tiny little movement that it's only the photocenter which is wobbling, we get those binaries as well. Planetary systems, Gaia will be very good, not in Earth mass planets, but very good in Jupiter kind of planets, which are far away. It's really a sort of parameter space area where it's very difficult to do it from the Earth, or you need a lot of patience to do it with the radial velocities. And Gaia will be astrometrically very good in that one. So Jupiter in an orbit of 10-year periodicity, that will be really something where Gaia will be very, very strong. Solar system, we will improve all the asteroid orbits, but we are also looking inside the Earth orbit. So we are going to see all these asteroids which are locked onto the Earth orbit, which are so far one of those have been found. Half a million quasars, so we can, in the end, we can connect the radio frame into the optical frame. And we have to do relativity, so we have to do it. So then we can do also experiments and what we do with, as an example of fundamental physics. We have tuned our scanning law, the initial conditions, in such a way that we happen to have a bright star close to the limb of Jupiter, 2017, and we are hunting the quadruple moment gravitational bending of light with Jupiter. That's a sort of nice to do, because we don't have any other constraints for the initial conditions. So we said, let's do that and optimize it that way. And this is the site where the astronomy information, ESA is a little bit confusing with the web information, so it's the Cosmos site, which is meant for the professional astronomers. Just very quickly, what it looks like schematically, 2 telescopes, 1 focal plane. So we get the images from 2 parts of the sky, and we mix them in the focal plane. That may sound very confusing, but I come to that, why we do it. And this is what it looks in reality. It's only silicon carbide, because it has very good thermal properties. It's almost as hard as diamond, but it has very little reaction to thermal changes. It happens to be exactly the same size as the Herschel mirror. Not by accident, because it was braced in the same oven. So it just fitted there. CCDs, so we have a focal plane, which is 1 meter by half a meter roughly. And how the Gaia, very quickly how it works. We are scanning the sky, and we are reading the CCDs with the same speed as we are scanning the sky. So that's the way how we keep the images all the time sharp on the focal plane. The only thing where we are not mixing, excuse me. Where we are not mixing the 2 lines of sight are the sky mapper part, where we are viewing the full sky and deciding when do we have a point source what we are going to observe. When we have made that decision, we are checking that our decision was correct with the first row of the astrometric fields. So in case we have some cosmic radiation hits, that's the way when we throw them out, because we didn't see the same hit anymore at the first row of the astrometric detections. Anything that has passed, we observe only that tiny little window on the CCDs through the whole focal plane. We do photometry in blue part, we do red photometry, and then we look into the red photometer data, we look the wavelength coverage of the spectrometer and make a new magnitude estimate and decide if the star is bright enough, we do also spectroscopy. If it's faint enough, we don't do it. If it's bright enough, we do it. And that's basically the principle how we detect the full sky. And it's the first sky mappers where we have the bookkeeping from which telescope the star came. Because after that, it's all mixed. And this is the kit, which is now in L2, 1.5 million kilometers away from us, flying happily and all working. Just very briefly how Gaia is doing the scanning. We have 3 movements. First of all, the constraint. We have a 45-degree tilt to the sun, and it has to be always 45 degrees because we don't want to have any thermal changes in the payload. We want to keep everything at the same temperature. With this 45 angle, we are spinning with 1 spin taking 6 hours. And then what we are doing, we are precessing the spin axis. So we are spinning, precessing every 63 days, and we go with the L2 around the sun in 1 year. And it's the combination of those 3 movements which gives us the coverage on the sky. And it looks a little bit peculiar, the coverage on the sky, because we want to achieve that we are scanning all parts of skies, not only as equal numbers as possible, but also always with different directions, so that in the end, when we get the parallaxes and proper motions, our error bars are roughly symmetric and not with some sort of elongated shapes. Just a few pictures of the hardware. Just before the launch, when Gaia was in a sort of folded configuration coming to the site, it was put on the frigate, which is the last stage of the launcher. And that was, of course, one of the critical things when we had to open it. And a lot of gray hair from that one that we were ensured that it worked. And if I look at the animation on JWST, it looks very exciting because there are so many moving parts that I just hope it all really works. I was closed. Our quality person was the last one who put the head from the hole and ticked the box. Gaia is in, and then we closed it, put it on Soyuz, which I mean, it's also one of the most peculiar experiences in the project is to sit in a launch readiness review where the meeting languages are only two languages were spoken, Russian and French, and I was the only person who had headphones all the time on because I couldn't understand anything what was decided. But it went fine. We launched in December 19th. Everyone wanted to go Christmas home, so there was a real push to do it, and we didn't complain. Now, how are we doing? Just sort of selection of various things what we found from the commissioning phase. We have a normal chemical thrusters where we can do all the orbit maneuvers and everything, but really for the astronomical work, it's the micropropulsion which is the key thing. That is to keep exactly the spin synchronous with the CCD reading. So to us, it was really important that the micropropulsion system is working well, and overall that the attitude and orbit control is working well. And just to demonstrate it in a graph, we are looking for the deviation from the nominal spin speed. And what will happen is that there is a small noise which is really at the insignificant level for Gaia accuracy. Every now and then, as we knew already in advance, we get a hit by a micrometeorite. So we get an impulse impact on Gaia and it starts to move. And what we are doing on board, we are reading the stars between 13 and 16 magnitude all the time, and we are measuring, do we see the star in this CCD and the next one when we expect? And if we don't, we know that we are spinning with the wrong speed. And we have to put a loop which goes to the microthrusters at the level of micronewton thrusts to correct for it. This is a rather big micrometeorite, so we overshoot a little bit before coming back, but within a few minutes it's done. And these kind of big things we only have once a day or less. And the smaller ones we correct much quicker. The phase array antenna is also, because we are at 45-degree angle, we don't want to have any moving parts. So it's totally electronically steered beams. We are changing the beam all the time, depending on how Gaia is spinning. And there we have healthy budget, so we get all the data down as we want. Rubidium atomic clock to get time stamping is working fine. And we haven't lost any CCDs. They all work, and they also work that the electronics so that we get the window exactly where the star is. When we store the star, it goes into the memory. If memory is full, we get the right priority order, that the low priority things are deleted if needed, high priority ones not, and we are connecting to the ground station. We get the high priority star packages down first. So all that is working fine. Then I want to just take a little bit sidestep a few things just to indicate that in this kind of big project you might have elements which are sort of invisible, and there are groups of people who are working and putting a lot of effort and serious scientific thinking and work to get it right. One of the things what we have to do, we cannot with traditional tracking methods know the orbit of Gaia accurately enough, because our requirements is we need to know the speed, velocity of Gaia to 1 millimeter per second. And we want to know within 150 meters where the spacecraft is. That cannot be done with the traditional tracking and ranging methods. So what we do, we are looking with the optical telescope every night where Gaia is. So there is the track, what we have been doing in the first year. We observe it nominally at 20 milliarc second position, and we feed that one into the orbit reconstruction. Then we know Gaia speed with 1 millimeter per second and 150 meters positional accuracy. Unfortunately, there is no stellar catalog at 20 milliardsecond level. So what we are doing, we are observing, put it in a storage. Soon we are going to make the first Gaia catalog. Then we will have a Gaia catalog of stars, which is at the 1 milliarsecond level. Then we will re-reduce all the data. Then we know where Gaia was. Then we will feed that one back into the orbit reconstruction, because now we can really correct it. And then we do the reduction again. So there are a few steps like this. And it's a big group of people who are doing this. And taking it really, doing it properly is necessary.
How faint is Gaia? I heard it was fainter than expected.
It's faint. It's 20th magnitude. So we can do this one actually. We're hoping to do 1 meter telescopes, but we are now at the ESO 2.6 meter telescope. Otherwise, it's too faint.
How long can you go without, if you have a run of bad weather, so you don't get optical updates? Can you go a long time and still, not be too worried?
We are doing from ESA side a tiny little security measure. We are observing it also with sort of kind of VLBI method, but not directly. So for the first year, we have put a lot of time to have a double coverage, the optical one and the VLBI. And after the first reduction, I hope that we can really say that can we give up the VLBI part, because there we have again then competition with like Rosetta. I mean, it's very difficult to argue that Gaia needs 2 ground stations for position measurement if Rosetta wants to do something spectacular. But so far we have managed. So it's a valid point. Relativity. So in Gaia accuracy, the solar system is like a sort of ski slalom field. It's a gravitational field with all kind of curves. And every photon, it doesn't come to Gaia straight in the Gaia accuracy. It's making all these curves and turns. And in order to know where the star is, we have to backtrack it. So for every light, we have to do the relativistic calculation, how the light has been bending on the way before coming to Gaia. And of course, the problem is that 5 minutes later, the planets have moved a little bit. So we have to do the calculation again, because otherwise it doesn't match anymore. So there's an enormous machinery to do relativistic calculations efficiently enough that we can cope with all the observations. Again, a big group who is only worried about the relativistic effects in Gaia. And then we have like ground-based observations continuing to monitor that our radial velocity standards remain standards in the timescales of 10 years, and not only that they happen to be constant for the 5 years before the mission. Now, not everything is fine. There are also always unpleasant surprises. So I have listed here the 3 main ones which are related to astronomy. We have stray light. So this is sort of omission in the design. We get some astronomical sources, but especially the nasty one is the sun. We get regularly the sun stray light into the focal plane. And what turns to be the case, at the edges of the sun shield, where they are cut, there are fibers sticking out, and these fibers scatter light. And we could eliminate the fibers from part of it. We were putting tapes, but because we had the configuration where the MLI was, where the sun shield was rolled in, we couldn't tape all the edges. So we knew of the fibers, but we didn't think through that it might be such a bad issue with the stray light, so we left them. Because also you don't want to cut fibers in a clean room, because you might get all the stuff in your telescope. So here we have extra background light, which impacts the very faintest sources of Gaia. Another surprise what we have is we have still water coming from somewhere. And at the beginning of the mission, we had really ice coming onto the mirrors, and we know it's ice because we heat it, and at the temperature where ice sublimates, it all went out. It even went out from the 2 apertures in such a way that we saw when Gaia was tilting when it got rid of the water. But there is a little bit coming back. It's now very slow, but it's still not exhausted. And finally, what is still on the table is that I mentioned we have these 2 telescopes, and the whole construction is, of course, you have to know what this angle between the 2 telescopes is, otherwise your whole idea collapses. We knew that there will be variation. So there is a interferometry metrology device which is measuring this. So we are measuring it with accuracy below 10 microarcsecond. But the variation, the amplitude of the variation is larger, and it leaves a bit uncomfortable feeling. So you would like to understand at least what is it all about. So what do? The stray light, unfortunately, we just have to live with it. So what we are doing at the moment, we are, especially the spectroscopy, we are changing from readout noise limited domain into background noise limited domain. So we are making onboard software changes, and we are just putting it uplinking it around the coming weeks to make the new version to test that everything works. For the contamination, we have last time heated the mirrors in September, and then we got full recovery of the transmission. Everything changes a little bit thermally, so we had to do tiny little focus correction in October. And now we have decided that mid-May is the time we have to do again a heating. And we heat the mirrors, get rid of the water, and then we see if it comes still back. And for the basic angle, we have still our industrial partner on board, and they are having a big team of engineers who are doing now a full modeling of the whole spacecraft together in order to understand what is happening at the basic angle variation. And it's a very tricky engineering problem because we are talking about nanometer changes in a structure which is meters. And that makes it very complicated to do the modeling properly. Now, a little bit of data. This is not Gaia data. This omega sen as seen from the ground. And if you put omega sen through Gaia, then suddenly you start to see in between the stars. So sky is still black even for Omega Centauri. And just to show what was there when we scanned over, this is not an image, it's a plot. And what is plotted here are on board we make this detection of stars, and then we follow the windows down. So what is plotted here are all those wind detections, what we said that there is a star, and then we just put a dot here. So one can see that we still recover the omega sen. It's also, one can see that we do get the resource shortage at very close to the central part. We are missing sources because there are just too many sources in one line of the CCD. So how do we recover this one that's the thing why we observe everything 70 times. Because when we are crossing this area with different angles, there will be a variation always, where do you run out of the resources? And in the end, we recover all the sources. Photometer, just the design, we had split into two parts, blue and red, and then with the prism within these bands, we disperse the light in order to get higher resolution. So actually the photometric device is very simple piece of glass with good coating. And before the mission, we were making lots of simulations of what is the spectral energy distribution of stars when they are at different temperatures. And sort of what one is getting at the 15th magnitude, we are talking about extinction reduction to 0.1 magnitude, surface gravity, metallized to 0.2 dex, effective temperatures to 200 Kelvin. Of course, for individual 15th magnitude star, this is not impressive. The important thing is that when you have this for 50 million stars, then suddenly you can do something very useful with it. These are simulated data, and this is the real data. Well, happens to be same people. They seem to like the same colors to plot. So it looks more or less what the simulations. These are brighter stars, so just the one photometry point, and you could immediately do the spectral energy distribution. So it looks like the data is coming like simulated. So the performances what we anticipate to get are those ones we thought before the launch. And this is just the blue part of the same stars. Radial velocity. What we are doing here is a wavelength range which covers the calcium triplet region of the spectrum. The spectrometer is a specific box with lots of glass and rather compact and tight configuration of lots of lenses and wedges. and it's sort of hanging upside down at the bottom of the payload element of Gaia. And when we do spectroscopy, the first thing what we did was, of course, to look at, okay, something we see of bright stuff on the ground, do we get the same with Gaia? Well, this one is then degraded to the same resolution as with Gaia. And so the instrument itself says what is the main thing, is the radial velocity spectrometer. So it's really the dynamical part which is the intention. However, when you have bright stars, you have enough photons, enough signal to noise, and then you do just spectroscopy. So the estimates are that when you can do really sort of atmospheric parameters, rotational velocities, then we are talking about sample of about 5 million stars to 12th magnitude. And if you really go to abundances, then maybe 11th magnitude is the limit. So we are talking about sample of 2 million stars. So these are nice side products of Gaia. The radial velocities, we are talking about 100 million stars, which is really the main thing of the spectroscopy. And just to look a little bit at how does it work. So we always have this same wavelength range. There is no tuning that if the star is different, we do a more suitable wavelength regime. No, it's always the calcium triplet, independent whether the source has any calcium triplet lines or not. So for the cool stars, it works, of course, fine. I mean, you have either other lines, which you can use in the spectral matching to get the radial velocities, or if you have anything like K, G, F star, you have the calcium triplet line, so it works really optimally there. When you get to hotter stars, then it gets more difficult. You do have some hydrogen lines, but clearly much broader, so consequently also your radial velocity determination is not going to be for hot stars as good as it's going to be for cool stars. It is a choice what was made. Most of the stars are red, so if you are choosing that wavelength range, you end up with significant radial velocities for a large amount of stars. And finally, just a demonstration of the capability to do some variability studies. What we have done at the beginning of the mission for calibration purposes, I mentioned that we can precess the axis, but we fix the axis in such a way that every scan crossed the ecliptic poles. And the advantage was that we had been doing a lot of preparatory work in the ecliptic poles, so we could do a calibration purposes. And then for variability, it happens to be that anything in the ecliptic poles, we did it for 1 month, so you have 2 telescopes crossing the field every 6 hours for a month. So you have a lot of data from a few stars. So what we looked some RL-Lyra stars, which have been discovered by the OGLE survey. So it's really testing that can Gaia do it. And well, first of all, I think when we use the OGLE periodicity and phase fold all the light curves, we get exactly what expected. What I think is worth noting is that Gaia's limiting magnitude is 20. Very often if people have, our survey stops at 20th magnitude, then the data quality at 20th magnitude is not high. We are here very close to the limit of Gaia, and I think that data quality, every point is a single epoch transit, is very good. So the quality of the Gaia data down to the limiting magnitude is going to be good. And then just to say that the science alerts, also they were successful. We got one supernova already last summer. So it was just based on that at some point the source was at 90th magnitude, and a little bit later we get it at the 70th magnitude. People looked at blue and red photometer, looked like a supernova. But before we went public saying that Gaia has detected the first supernova, we wanted to be a bit sure. So we did go to a ground-based telescope, and galaxy which used to look like this, looked like that. So then we were pretty sure that we have discovered the supernova, and we could go public and tell that Gaia is able to do that one. At the moment, the science alerts stream is really struggling to get. The main problem is to find all these pairs that you associate new sources to the old ones. So they have still some work to be done so that the stream start really to produce. Because we expect to get, as everything is running nominally, maybe few bright supernovae every day, and 6 or so fainter ones. And sometimes you get then things you didn't think about or didn't even want, or first you thought that you don't want. So just sources in a very peculiar pattern, but if you look why the pattern was, it's the Cat's Eye Nebula, and it's just, we didn't think about it, that of course, I mean, if you have sharp enough edges, they look like point sources. So there is no science case for Gaia to do expansion velocities on the sky of planetary nebulae, but I think somehow that will be possible as well. Now, the performances, where are we? Taking into account the stray light contribution, so now counting that one, which affects especially the faint stars. So the astrometry at the bright side is still unaffected, and at 20th magnitude we are still sort of at half a milliarc second. I mean, this is just for one type of star, it's a solar type, unread one. Photometry, millimagnitude domain, end of mission, going to 60 to 80 millimagnitude at the faint end. And the spectroscopy, where we have the highest hit at the faint end. So we are now at the sort of limit where you say that, well, this is still a useful radial velocity accuracy. We are at the 15.5 magnitude. Few words of the data processing. So I already mentioned at the beginning that it's done by the scientific community and under this DPAC consortium name. It's pretty well across whole Europe where we have participants. We have something like 450 participants nowadays. And if one looks at the countries which have a lot of participants, there you have a little bit of engineering also, because in Cambridge we do the photometric processing. In Toulouse, CNES Center, we do the spectroscopic, astrophysical parameters, binaries, and solar system objects. In Turin, we do modeling of the astrometric instrument. In Barcelona Supercomputing Center, we have really a sort of reprocessing of the initial stages. And in Madrid, which is the ESA center, we do the astrometric solution. So in those countries, we do have then more participants because they are also really the operational centers where all the calculations are done. And what is the job they have to do? If you do the mathematics, every object observed roughly 70 times over 5 years. So you come to an average day that every day we have 40 million stars observed. That's more or less what we are getting, 40 million in a normal star. And because every star is sort of seen in all these rows, so we're talking about 400 to 500 million measurements coming down daily. And we had just now the busy time, we were having scans which were at the galactic plane. So we were all the time at the high density region. So 28th of February we got our record. We had 270 million transits in one day. So we had 3 billion measurements in a single day. We have already collected 3 billion spectra in the database. I think it's the biggest spectroscopic database what exists. And just a little bit of credit to the people who are doing the science alerts. In an average day, 40 million stars with a Gaia accuracy, about 10% are variable. So every day we get about 4 million variable stars. So out of these 4 million variable stars, the one supernova, it's not so trivial. It is a bit tricky to identify that one in a quick and efficient way. So we knew that we will observe a lot, but I think it still took us a bit by surprise. Data releases. The photometric science alerts, as I mentioned, they have started. The first thing what we are aiming now is to have a summer 16, just the positions at that stage. We don't have enough data really to have a reliable separation between proper motions and parallaxes with not having sufficient amount of data. To get the broadband magnitudes, and then we can do, just if you have a position, we can look at the Hipparcos stars, and we can do the proper motions. So it will be a proper motion catalog for bright stars. And then I mentioned the ecliptic pulse data, where we have lots of sightings of a small area of the sky. We try to get that one out too. It's most likely now that I mentioned that we do this decontamination middle of May. So it will be, this release is most likely then going to be the data up to middle of May, roughly. So that will be a sort of stopping point to us, and we try to produce a release out of those data. We believe that only half a year more or so data needed, and then we can try to do really that the parallaxes and proper motion start to be separated. And early 17, we are looking into 5-parameter astrometric results, bright star radial velocities, integrated photometry, and then with the time it gets of course a little bit hazy that what when precisely, but just to give that what eventually will be. So we will give astrophysical parameters. Of course, it's not going to, you shouldn't expect that Gaia will say that that star is an F3 star. It will be more like a probability distribution. So the work with Gaia data will be quite different in a way. If you are doing sample studies, then you also, all the sample individual objects have probability distributions rather than saying that this is of that spectral type. One wants to get spectra, constant radial velocities, and also some binaries we start to get early. Of course, many of the binaries will come much later because you need the baseline to see that something deviates from a single star. And so on, variability, solar system objects, and multiple objects. We are doing a lot of tests at the moment to see where we precisely are, so that's why it's a bit vaguish, I would say, but please bear with us. As soon as we fix that, okay, we know precisely where to go, we will make it public that what we can do. Now, going to conclusions, just what are we observing at the moment? So we have fine-tuned, originally Gaia was supposed to be working from 6th to 20th magnitude. So we have fine-tuned the parameters on board, and we now observe stars starting from magnitude 2 up to 20.7. So it's not anymore a billion star survey, but maybe 1.5 billion star, remains to be seen. The very bright stars we cannot get. They are just so saturated and so big that the detection algorithm cannot find them. So just to be complete, it's more for the beauty. We are collecting these tiny little images of all the bright stars because we know where they are accurately enough. We have no idea how good astrometry we can do with the very brightest ones. Maybe milliarc second, maybe not. But now we just collect the data. So then, in that sense, Gaia will be complete. So all the bright stars to 20.7 done. The spectroscopy we get from second magnitude. So that one we can only do where the normal system finds that there is a star. So we cannot do the very brightest, but it doesn't really matter, spectroscopy for the very brightest ones. I mean, that's nothing new. So that's what is done. The faint limit of the spectroscopy might change still, because I mentioned that we are having the software, what we are now testing, which is really meant to mitigate the stray light problems at spectroscopy. So depending on how successful, how well that works, we may do some fine-tuning here, but I don't expect big changes, if any. So we are a little bit juggling here because we had this big galactic plane scan in February. We will have another one next month, and we are testing software. We don't want to test the software when you have 200 million stars in one day, so we are trying to a little bit juggle with the schedules. We are happy to decontaminate in the sense that we need a little bit of breathing also, think about the data and process it. But otherwise, we don't want to decontaminate too often because it disturbs the thermal balance of the satellite. We are looking forward to that the basic angle variation industrial studies are completed. And then we should really, by summertime, start to consolidate, really tell the community when the data is coming and what we are precisely going to put out. And I just want to finish with, this is my last slide, and I just want to put a rolling sort of idea of these three movements, what I said, how Gaia is scanning the sky, that you can get an impression of how the data is being collected. And I leave it running, and I stop here, and thank you for your attention.
help understand. I heard a while back that VLBI measurements of the Pleiades gave a result which differed from Hipparcos by something like 10 times the quoted error of the Hipparcos determination. And I also heard that Gaia was going to use the same, whatever it was, software reduction method or data taking method that Hipparcos did. Until this was understood, there was a problem. I was wondering what the status of the solution to that problem is.
I prefer that status to be sorted out by Gaia data, and because in Gaia we see all the individual stars, which and we can get really the three-dimensional structure of Pleiades. However, let me comment anyway, because I think the Pleiades discussion has been rather disturbing, I would say, in general. The way how, I would not call it very scientific, how the discussion went not only to scientific journals, but it went into all kind of newspapers and in all kind of steps. What I see, I accept, maybe Hipparcos is wrong. It could be. But the work what has been done is a very thorough work. Of course, always some assumption may be wrong, that it doesn't match. Now the latest one, the VLBI work, I was less impressed of it. I don't say that it's wrong. It could be right, and Hipparcos could be wrong, but if you look at the 5 stars, what was done with VLBI, there is a fit to the observed motion for parallax, proper motion, and acceleration for binarity. You get the parallaxes which fit the traditional Pleiades distance perfectly. If you look at the proper motions have very small error bars corresponding to spatial velocities of 0.1 kilometers per second. Pleiades velocity dispersion is 0.6 kilometers per second. And the differences of the proper motion in that paper are, in some cases, 5 kilometers per second. There is something very odd. The proper motion distribution of these 5 stars after that fit is much bigger than what one would expect from Pleiades. Now, it may be still that the parallaxes are correct, but the fit is odd. So I think that it would be better to try to do better work in areas rather than going to publicity and seeking dilemma which doesn't exist. I'm perfectly happy to take with Gaia Pleiades to any distance what the data shows. I don't know if that satisfies
You
it.
do the Gaia observations early on to check whether you agree with the Hipparcos or the
It cannot really be done because it's with Gaia we have to do a global solution. So we do the whole sky or we do nothing. It cannot be done like a separate mini project. It will come out as the first solution, and I think the issue will be settled.
A science and a hardware question. Is there the possibility of an extended mission beyond 5 years? And if so, how would your constraints improve with time over the 5-year baseline? And the hardware question is, you mentioned that Gaia is struck by a micrometeorite once a day on average. So over a 5-year mission, that's about 1,500 or more of these. What effect does that have? Presumably they go through that sunshade, which is just MLI. Does that affect the stray light over time?
Yeah, that's the favorite discussion first. That we have a hole, and that's why we have stray light. You get hole, but there are several layers,
Right.
so the likelihood that that will happen, it shouldn't be too big.
Sort of baffled.
Yes, so I don't think that one is.
The extended mission.
The extended mission, but of course it's always, if everything works. I mean, you never know, maybe tomorrow something happens and it doesn't work. But basically what really will limit is this cold cast what we use for the micropropulsion system. And if I look at the daily consumption of that one now, I will predict a mission time which is beyond 10 years. However, we know that the sun shield will suffer from the solar impact, and the torque from the sun will be growing with the mission. So we have to use more the gas in the future. And we are not yet seeing clearly that increase in the consumption to make a prediction that are we talking about 6-year mission or 8-year mission. But something like 6 to 8 should be possible, even with current knowledge. But probably not 10, but who knows. And sorry, the improvement thing, especially it's important now because the faint ones we can improve. For the bright ones it doesn't really improve anything, but for the faint ones it would really benefit. We would really get the stellar impact diminished in that way, just collecting more data.
Are Gaia positions going to be tied into the ICRF, or, I mean, are you going to be improving the ICRF significantly with Gaia results?
Gaia will be totally independent by itself, so it will be a solution which is then rotation-free. So we can rotate the system as we wish. Of course we will rotate it to something sensible, and it makes sense to rotate it to ICRF. However, there is currently actually one of these behind the scenes, there is a big group of observing quasars, because it's not at all clear that the radio center of a quasar and the optical center of a quasar coincide. There is probably at the sort of level of 30 microarcseconds some noise. We are trying to select the quasars which are as compact in radio as possible and do the rotation in that one. But this may be a limiting factor. It may be that the Gaia system itself and the ICRF itself are more accurate than we cannot combine them with the same accuracy as they are independent.
In the regions where it's too crowded to keep all of the sources, like the Galactic Bulge, how do you decide which ones to keep and which ones to throw away?
It's a priority order by magnitude.
So it's just strict magnitude.
Straight magnitude. There was a heavy discussion in our science team because we have an option that after 16th magnitude we randomize. So then you don't have as many visits per star, but you have all of them more or less. But we decided that it might be so crowded region, it's better to get those stars where you have flux, do them properly, and then maybe your limiting magnitude there is 18 and 19. One more thing what we do with the imaging, just in case, again, to our back pocket. Every time we cross Bares window, Omega Sen, and a few of these high density regions, we also make an image and put it in the storage, and we worry about it later, but we have it. And then we have the 21st magnitude everything.
So you mentioned near-Earth asteroids briefly. How well do you do with rapidly moving objects?
We will be very incomplete. So it's really a question of luck. If it's in the line of sight and doesn't move with respect to Gaia, because in Gaia only stars will remain point sources. Anything what moves in that reference frame will give a streak. If the streak is small enough, we will get it. If it's too big, so the velocity is too high, which is high probability for near-Earth asteroids, we will miss it. But those ones which we will get, we will predict precisely where it will hit the Earth. But of course, we are never going to tell because we have data rights issues. To be first published scientifically.
Jonathan in the back.
So if you set the spectroscopy limit to 16.2 or whatever, am I understanding correctly that then even for an emission line object where you might be able to see it if it's fainter, you're not going to get the data?
That's correct, yes.
Yeah, so my faint AGN, survey, or anything like that, forget
Yeah.
it.
That is also the big answer that we don't quite know. The estimates of how many galaxies we get vary from 2 to 10 million. We don't know because exactly all this kind of emission line issue, little bit extended, and then how the algorithm works because it expects a point source, and
Yeah.
so we'll see.
You mentioned the fact that you need to make generativistic corrections in the solar system, but can you comment on whether you can test generativity better than other tests we have, either in the solar system or in the galactic potential or some other test of generativity? What can Gaia do?
It's always a dangerous topic in the sense that all the tests are just at the limit. So if everything works perfectly, we can test many things: the gamma, the post-Newtonian parameterized formulation. We could do gravitational waves.
How would you, could you elaborate? How would you detect gravitational waves?
It gives a certain pattern to astrometry. So you have to correlate a deviation correlated over the sky. It gives a pattern, but Probably not.
Yeah, so my question is actually related to that because you talked about how you had to do these corrections for the planets that we know about. So is it possible that Gaia could put some interesting constraints on things much further out? Say a Jupiter mass object at, say, 500 AU.
That's very you really need a chance. It's
Well, you would have to rely on the parallax or the motion of the object.
yeah.
It would produce basically a ripple
Yeah,
on the
this-
background that would change with time. And if that ripple is large enough,
It's
I think that's what Roseanne wants to talk to you about, right?
yeah. We haven't really thought about that specifically. whether
7
it's-
microarc seconds for a Jupiter mass
Yeah.
for one source.
Yeah, I think in a way the whole category of microlensing is going to be quite an interesting thing to find something which positionally suddenly makes a jump and moves.
Go ahead, Paul.
So you mentioned some numbers about the I guess the relative photometry errors, and how do you do absolute photometric calibration?
In the end, it will be done to standards, but for the rest, Gaia is doing just an internal calibration. So we try to see all the variation from CCD to CCD for the same stars, because we see all the stars so many times, so we can really map the CCD sensitivities with Gaia data itself. And then when we have internally consistent system, then we basically it works. It's the second time I dropped it. Very solid hardware.
Light tested.
Final question?
Just a naive question. What is the smallest parallax that Gaia will be able to measure?
Theoretically, the smallest parallax error is something like 5 microarc second.
Okay.
But let's first get the systematic. Before we see that. I think in that domain, it becomes really important to understand the basic angle variation.
So you can really do the whole galaxy.
Yes, well, to the galactic center in a way.
Yeah.
It's good. But behind that, you see anyway very little because of extinction. Mm-hmm. It's half of the galaxy, including galactic center, is okay.
Well, Timo will be here for a little while today, and then tomorrow morning if anyone else has further discussion. But thank you again for